around kind of up in the foothills.
Very nice. So when should I start? Not yet. Is there a clock somewhere here?
Yes. It will turn into a clock. That thing will turn into a clock. The right thing there. At some point it will stop. It's trying to fire a signal.
Okay. Is this big enough, or can I write smaller than this, or that would be dangerous? It's about right? Okay. No. Not sure if we're waiting still for.
Yeah. So, pleasure to have Joao. Telling us about the logarithm.
Okay, thank you very much. It's a pleasure to be here. So, just some brief comments. So, the outline of this course, it's very obvious. So, I'll just discuss a bit some extra points about conformal field theory that David didn't mention, and that will be useful for my course. But that will be fast. We should finish today. Then I'll discuss more in detail the physics about anti-de Sitter space-time, so to get some intuition of what happens when you study dynamics or quantum field theory in anti-de Sitter space-time. And then once we understand that, it will be clear that there is a natural map between the two parts, and so we'll state the idea CFT correspondence, and we will discuss some of its applications and some of its particular realizations in string theory. And so that's the basic plan of this course. So I put some preliminary and incomplete lecture notes online. I don't know if you already saw that. So your comments are most welcome. I hope to improve the notes based on that. either by talking to me directly, so I'll be around all week, so please come and talk to me, or you can also send me an email about that. And of course, during the lectures, please interrupt, ask questions whenever you have doubts or something. Okay. Very good. So I'll just start with some very brief motivation. Which basically will be just a picture. So on this side, I'll draw conformal field theory. And so why should we study conformal field theory? Well, by now you should be convinced. David already made 1 week of propaganda. So of course, well, you can study continuous phase transitions. Well, this is not going to work. Okay. Well, you complain when I write too small. So essentially to study critical exponents in statistical mechanics or quantum critical points in condensed matter. So this is actually a very concrete physical application of conformal field theories. Then there's another very important application of conformal field theories, which you also discuss, which is the notion that conformal field theories are both the UV and the infrared limit of RG flows. So essentially they define what we mean by quantum field theory on the continuum. You always start from some conformal field theory and then you flow to another one, or even to the trivial one, to a gapped phase. So this part you discussed last week. We want to study conformal field theory. Now I want to draw here the other side, which I'll call quantum gravity in AdS. So why should we study quantum gravity in AdS? It seems that we live in flat space, or, well, if you want to think about cosmology, we live in de Sitter, not anti-de Sitter. So why anti-de Sitter? So there's actually very good reasons to study quantum gravity in anti-de Sitter. Okay, the first reason is that anti-de Sitter space is like a box. Okay, so why is this relevant? So I mean, this will become clear throughout the lectures, but here I want you just to get the main philosophy. So why do we want to study quantum gravity in a box? Well, first of all, you have a gapped spectrum. So that's good. You get rid of lots of infrared divergences that you have in flat space. So it's better defined to study gravity in this background. Another reason is that you have stable black holes, thermodynamically stable black holes. So it's also, if you want, it's the usual story, right? If you want to do statistical physics, you put the system on a box and then you do thermodynamics. Right? That's the first step. So that's another reason. And a related reason is that since this is a box, you have actually a time-like boundary where you can probe the system in a very well-defined way. Okay, so I should draw the usual picture. So AdS is the interior of some cylinder where time flows upwards. And then the idea is that if you want to study quantum gravity, you can be an experimentalist outside. Okay, and now you go and you probe your system, you send something inside, and then you observe what's coming out some later time. So you have this very controlled experiment over, well, if you want, it's a sphere that you have in the lab, and now as time goes by, you can perturb it and see how it responds to your excitations. Okay, so in particular, you can create black holes inside, see how they decay, all this kind of story. Okay, so So by themselves, these two things would be important, and they existed before AdS CFT, this kind of study completely unrelated. Now the goal of these lectures is to convince you that they actually are the same thing. They are equivalent. And when you understand that, you make a lot of progress. So in particular, you make a huge progress in this direction, because now you can use your conformal field theory, which is something completely well-defined quantum field theory that you learn axioms from David last week. So this gives you a precise definition of quantum gravity, okay, in anti de Sitter. So for example, questions, so here, a priori, you only know how to do some effective description of, say, some graviton scatterings at 3 level, or some semi-classical analysis of black hole physics, because you don't really know how to make sense of the quantum gravity in the full quantum regime. But once you understand this equivalence, then the CFT is the precise definition, okay? So you can ask questions about black hole evaporation, like the information paradox. All these questions become very concrete questions about this CFT, and that helps you make progress. Okay? You also gain a lot in the other direction. Here, I would say it's more on the qualitative side, because basically what this map gives you is that lots of complicated phenomena in conformal field theory, especially if they are strongly coupled, become some more intuitive geometric concepts on the gravity side. So I would say this gives you geometric intuition. About lots of quantum field theory phenomena that I'll discuss some examples. Okay, any questions about the philosophy? Yeah, you guys are very pragmatic. Very good. No waste. We should not waste time with philosophy. Okay. So where should I see the time then? Sorry,
this screen eventually.
Eventually. It says here 9:12 on top. Okay.
It will be a much more useful clock if you don't touch it for another few minutes. It would probably be good to figure out how to make it go back to that screen, but I haven't.
Okay. Okay, so let's start. Let's start with the topic number 1, conformal field theory. But in fact, what I'm gonna discuss now, it's much more general than conformal field theory. It's true in any quantum field theory. I'll be interested in this context. But
There you go. Now the clock is there.
Nice. Okay. Okay, and it's the idea of large N factorization. Okay, so I want you to consider UN gauge theory. And I'll write schematically just the action in the following form. So it will be a trace, and then I'll just write some fields phi, some kinetic term, and then some interactions. I don't know, phi cubed, phi to the 4th. Doesn't matter. So the structure of the action is just that it's just a single trace of a polynomial in these fields phi, where these fields phi are valued in the adjoint representation. And I'll use the fact that the adjoint representation, I can represent phi with 2 indices, say I and j, where I is fundamental and j is an anti-fundamental index. So both I and j run from 1 to n. Okay, so it's an n by n matrix, Hermitian matrix. And of course, I need to put here the coupling constant, and I'll write it as n over lambda, where lambda is just G Young-Mills square times n, It's called the 't Hooft coupling. Because it was introduced by 't Hooft. And now I want to consider the large n limit, okay? But the specific large n limit, which is called the planar limit, which is the limit when n goes to infinity with lambda kept fixed. How many of you already know this? Well, some people don't know it. Okay.
It's good. You should say this.
Good. Here I have this black hole problem. Okay, so I'll start here. So let's try to think about this limit in perturbation theory. So let's go to the propagator. So the propagator of this field, field phi. So let me say I have two of them like that, and I want to consider the propagator. But okay, I'm not interested in the space-time dependence. I'm only interested in the index structure dependence. That's what has to do with the large n limit. So this will be proportional. So first of all, since it's the propagator, it's the inverse of this kinetic term, so it's lambda over n. And then the index structure has to be like delta I L delta K J, right? That's the only UN invariant way of contracting these indices. And so the idea of 't Hooft was to say, well, if the propagator is this product of two delta functions that propagate the index, in fundamental and anti-fundamental indices, so we decided to introduce a double line notation where each propagator is represented by a double line, which is with some arrows. So the index I goes to the index L, and the index K goes to the index J. Okay, so this is the double line notation. Okay, so what about the vertices? So the vertices, well, here you can take any of them, but so they will be n over lambda times trace of some power of phi. So let's say phi cubed, for example. So it's also very natural to write these guys in double line notation. So the trace, well, maybe I should write it. So the trace of the product of three phi's, if you write the indices, well, you have I, J, J, K, K, right? So it's this cyclicity of the trace. So in this double line notation, it's natural to draw it something like that, where the index I flows here, then the index J flows here, and the index K flows here. Okay? Okay, I'm running out of space already. So let me start then putting this together into vacuum diagrams. So yeah, let me just draw these two examples, and then so let's say yeah, let's do this again. So for example, this has two cubic vertices and then has some propagators. Okay, this is one example. Okay, for now it's okay. And I need more space here. So let's try to be more systematic. So I want to study generic vacuum diagrams. So I'll say that V is the number of vertices, and then E is the number of edges, which is the same as propagators. And F is the number of faces, which is the same as lines, okay? These single fundamental lines. So for example here, this one would have, this one would have two vertices, right? A cubic vertex here, another one here. It would have 1, 2, 3 propagators, so 3. And how many lines? 1, 2, 3, okay? Sorry, let me explain that better. So you should also count, so the lines is easy to count. The faces, it's like this is one face, this is another face, and the exterior of the big circle is another face. Okay, so that's why faces are the same as lines. Okay, maybe I should draw another one just to, let me draw this one. Okay, so this one has 4 vertices. And how many propagators? Well, 6 propagators, right? 1, 2, 3, 4, and then these crossed ones. 6 propagators. And how many faces? 2 faces, right? Because if you actually follow these lines, they are just always the same line. Okay. Very good. So we know how to count. Very good. So now something a bit more general. So a generic diagram. How will it scale with n? Okay. So now that we did this accounting, it's very easy, right? So for each vertex, you get this power n over lambda. So this is number of vertices. Then from each edge, you get the opposite, because the propagator is inverted. It's the inverse of the kinetic term. And then you get a factor of n from each face, because every time you have a closed single line, that means that in that diagram there's an index I running from 1 to n, so there's a sum from 1 to n. Okay? Okay, and so now, can you read here? That's good. So now I want to write this in the following way. I want to write this as lambda to number of faces, n over lambda to the v plus f minus number of edges. And now you should recognize this as being the Euler characteristic of a 2D surface, okay? Triangulated by, not triangulated, like discretized by vertices, with vertices and faces and edges. So this is just, so this is the Euler characteristic. And it's basically, so of 2D surface. And what 2D surface? Well, the 2D surface where these graphs can be drawn, okay? So this is actually just given by 2 minus 2g, where g is the genus of the surface, which is just the number of handles. So it will be, the Euler characteristic will be 2 for the sphere, and it will be 0 for the torus, and so on, okay? So for example, you can check that these diagrams, this one obviously can be drawn on the surface of a sphere. This one, no, and if you go and check, you get the Euler characteristic being 0, so it has to be drawn on the surface of a torus. Okay? So why all this discussion? So the main point is that this, by doing this double line notation, you can immediately separate what diagrams, what Feynman diagrams, contribute at leading order at large n, okay? And these are the planar diagrams, because you see those are the ones that scale with the highest power of n. Okay, so planar diagrams dominate at large n. Okay. So yeah, I should write that somewhere. Right here. Planar diagrams dominate at large n. Okay. These are diagrams with g equals 0, with g not 0. Okay, so why am I talking about this? Why is it important? So now I want to consider what are the implications, the physical implications of this dominance of planar diagrams for correlation functions of my conformal field theory. So let's look at correlation functions of single trace operators. So by this I just mean there are operators, let's say O, which they are just a trace of some product of these adjoint fields. Okay, anything of that type with just one trace. So it's very easy to understand the large n scaling of this kind of products. So if I have n of this in a correlation function, well, essentially you see these single trace operators are very similar to the vertices of the original action. So in particular, if I just bring outside this factor and I'll just redefine my operators with n over lambda times O1, n over lambda times On. This is really exactly like with the same scaling as a vacuum diagram, right? Because each one of these guys is basically just inserting a vertex that existed already in the original action. Okay, so that means that this has the same scaling. So I can just write the expansion. It will be n minus 2g minus little n, so that comes from here, times a specific function of lambda that depends on the genus, and you have some sum from genus 0 to infinity. Okay, so this is the generic structure of a correlation function, an expansion at large n. So there's a few comments I want to make. So the first comment is that if you study string theory, this is exactly the same structure as closed string perturbation theory. Okay? If you identify, so this is like closed string topological or perturbation theory. If you identify G string with 1 over n, okay, and in fact there's also a correspondence between, so each one of these single trace operators that I inserted here corresponds in this closed string picture to an insertion of a vertex operator on the world sheet of the string. Okay, so if you go and see the counting of the G string counting, it's precisely that, and then you have a sum over world sheets with the sphere topology, torus topology, and so on. Okay, but now let's go to the real. Maybe I don't want to erase this already. I can erase this. But what is the physics? I still didn't tell you what is the physics. Why large n is important? The main physics is in that little n that appears there. So that little n tells you that if you look at correlation functions, at connected correlation functions, they are much smaller than the disconnected correlation functions. So actually, I should write here. So this discussion was just for the connected part of this correlator, because I'm joining all the vertices. So for example, suppose you have a 4-point function, 01 up to 04, okay? The full 4-point function is given by a sum of the disconnected pieces, so products of 2-point functions, so plus the other permutations, plus the connected the connected 4-point function, okay? And now this disconnected piece, if you go there, scales like n to the 0, so, right, at the planar level. The connected piece scales like 1 over n squared, okay? So what this tells you is that basically these single trace operators are free. They just have 2-point functions, and then the connected terms are suppressed at large n. And this goes through, I mean, it's not just for the 4-point function. For any n-point function, always the product of 2-point functions dominates the result. So this is large n factorization. So maybe I should that. So connected correlators over disconnected correlators, much smaller than 1. Okay. Well, usually, actually, you can really say it's 1 over n squared. Okay, so in particular, I want to discuss one particular consequence of this, which has to do with the physics of then multitrace. What happens if I consider multitrace operators? Okay, so for example, let me take an operator. Let me put an OTIL to distinguish, which is just a product of several single trace operators. Okay, so normal ordered product at the same space-time point. So a local operator defined that way. So let's just do this exercise. Let's look at the 2-point function of this double trace operator. Well, from what we discussed so far, it's clear that what's going to dominate in this 2-point function is going to be simply the product of the 2-point functions of each one of the constituents. Okay? All the rest, if you try to connect them to make interaction, will be suppressed. So here is just a product of OI at x and y, I from 1 to k. Okay? And now, okay, just to be concrete, let me say that these guys are OI are scalar primaries in a CFT. Good, thanks for letting me know. I'll try to do better. So what you get? Well, you just get the usual formula for the 2-point function of a primary, where the exponent is just a product of all of them. Okay. So what does it mean? It means that this double trace operator, so the dimension of this multi-trace operator, is just given by the sum of the single trace constituents. Okay. Plus corrections, but the corrections are suppressed by 1 over n squared. So maybe I should find a color here. Actually, this can be made. There's no color. There's some yellow here. So of course this can be even more generalized. So for example, instead of just having the product, you can put some derivatives here. I don't know, m derivatives contracted or something. You see, if you put derivatives there, then again the derivative will just act on the product of the 2-point functions in some way, and they will act here, and basically they will just increase the dimension. So essentially the dimension will just be the number of derivatives. Of course, to get for this multi-trace operator to be a primary, these derivatives have to be written in a specific combination such that actually this O tilde transforms as a primary. But its scaling dimension will just be given by the dimensions of the constituents plus the number of derivatives. Okay, so in other words, the conclusion is that the space of local operators in a conformal field theory, in a large N conformal field theory, has a very simple structure. It has the structure of a Fock space. Okay, so space of local operators in large N, in large N CFT, it has the structure of a Fock space, where you should identify single trace operators with single particle states. Well, single particle states, right? And multi with multi. Okay, so in particular, the multi-particle states are just they have the energy, which is the sum of the single particles, and they don't interact. Yes. Yeah, if you assume that they are primaries, you can always choose them to be orthogonal. If they have different dimensions, they are orthogonal, right? That follows from conformal symmetry. If they have the same dimension, then if you want the matrix of 2-point functions is some symmetric matrix, so you can choose a basis that it's orthogonal. A descendant. No, but in any case, you would have, this is a 2-point function, so as many O's or I's you put in here, the same type. So you always have this disconnected piece when things talk to each other directly. You mean if they are the same, O. Okay, but then that's actually okay, because you will have you'll have just a factor of 2. Right, because you can contract the product of 2-point functions like that and like that. Yeah, so that will not change this argument for the scaling. Actually, if it's the same, basically it will reduce just to even spin. Oh, okay, forget that. Okay, so here I'm stating everything in the language of conformal field theory, but actually this is a much more general statement, right? Probably what you should learn from this is not this statement, which is specific to AdS CFT. It's just a statement that if you apply this logic to, say, any confining gauge theory, SUN gauge theory at large N, this is telling you that glue balls are free. Glue balls don't interact. So glue balls propagate to themselves. If you have 2 glue balls, the interaction between them will be suppressed by 1/n squared, right? And actually, you can extend this reasoning also to mesons. So actually, this was the motivation of 2 from the beginning, was to create a theory where mesons were free. They would not interact with each other. So to compute the energy of a meson is hard, because you have to understand how a quark and an antiquark bound together. But then once you have a meson, it doesn't interact with other mesons. Okay. So this is the statement that you have this Fock space structure. So what time is it? Now I need to control time. Yes, I'm late. Okay, just one final comment. So if I consider the stress tensor, then the stress tensor comes from the action or from the word identities with a natural normalization. So in this case, it will just be n over lambda times all. I'll just write, so schematic will be something like that. Okay. So that means that if you look at endpoint functions of the stress tensor, actually connected endpoint function of the stress tensor, because of this extra factor, they will just scale all of them like n square. Okay, so this is something that we will see that comes naturally from AdS. So I just wanted to call your attention to this special fact about the stress tensor. Okay, I think I need to go on. So any question about this? So the only difference is that mu nu is not a single trace with the definition, with the normalization I used before. It has this extra factor of n over lambda, right? That's the only difference. So you just go to the formula, take the leading term, so g equals 0, and now this little n to the minus n is cancelled by that factor. So you just get n squared. Okay? So where should I go? Yes. So okay. So actually, I was going to propose some exercise for. So you can generalize this notion of large n factorization when you have matter in the fundamental representation. That's one thing. But even independent of that, it also works. So for a Wilson loop, right? That's what we were asking, right? For a Wilson loop, if you just have a single Wilson loop, so it's going to be a trace of some path order exponential. It's also going to be a single trace operator. If you want, it's just a limit where a single trace operator that has infinite number of derivatives inside, of covariant derivatives inside. So it works exactly like one of these single trace operators. Okay, so let's discuss. So now this is going to be not important for a while, and I'm going to change to another topic, which is this embedding formalism for conformal field theories. Okay, so you know already almost everything about conformal field theory. So this is just going to be a slightly different language of understanding what you already know. Okay, but it's very useful in this context because anti-de Sitter space also appears very, very naturally in the same formalism. So it's easier to make the connection. So you already know that the conformal group is just this. So I'm going to do CFT in d dimensions. So the conformal group is just this Lorentz grouping plus d plus 2 dimensions. And so, in particular, this group acts naturally in. So this acts naturally in Rd plus 1 comma 1. Okay, so the goal here is going to be to lift our CFT to this space, and then everything, all the facts about conformal symmetry will be transparent, will just follow from Lorentz invariance in this space. Okay, so how to do that? So the first point is that we don't want the full space because that's too big. So we will restrict to the light cone. Okay, so we'll take the light cone, which will be the space. So let's take points PA, which live in this embedding space, but let's take them to be null. Okay, so and in particular, I'll write. Okay, so the natural Minkowski metric, you take the null cone through the origin of this space. But this is still too big because, well, you have one constraint, so you need to reduce one dimension more to go to d dimensions where your CFT lives. So actually, what will be the physical CFT will be living in a section of this light cone. So I need to draw and at the same time write. So maybe I'll go here. So let me draw. So this is P0, so this is time in this embedding space. And now you have this light cone through the origin. Okay. And now the statement is that the physical CFT will live in some section. So by that I mean you pick one representative per each null ray. So you cut here somehow this light cone, and so in this surface, which is now a d-dimensional surface, that's where your CFT will live. Okay. So to be a bit more concrete, let's discuss one specific section of the light cone, which is called the Poincaré section. And so this is a particular section where you intersect this light cone by the surface, by the surface defined by the condition P0 plus PD plus 1 equals 1. So let me say this is PD plus 1. Okay, so here it will be something like equals 1, so it's some diagonal like that, right? So okay, so this is the Poincaré section. So why is this section nice? Well, first of all, because it's parameterized by a point in Rd. So let me write it. Let me choose a parameterization of this section. So I'll write my vector PA, which I'll split the okay, so this mu runs from 1 to d, and this vector x mu is just a point, well, it's just d real numbers, so it's a point in Rd. And so this automatically solves that constraint. It also solves the constraint that is a null vector. So it's a good parameterization of this Poincaré section. Okay. And moreover, if you compute the induced metric, So you just take the metric on this big Minkowski space, and you can put what is the metric induced on this submanifold. So this is, you just take dp, let me say this is PA of x, dPA of x, dPB of x, and you contract with the Minkowski metric in d plus 2 dimensions. You just get delta mu nu, dx mu, dx nu. Okay, so you should do this exercise. It's very simple. And so this is telling you that precisely this section has the geometry of flat d-dimensional Euclidean space. Okay, so if you choose this section, your CFT is living on RD. That's where we like to put our CFT most of the time. Sure. So okay, good question. So let's go slowly. I think I will answer that question. So let's consider a more general section. Okay. So what's the most general section you can consider? Can I write it here? Yeah, I can write it here. So let's consider here. Let's consider a general section. So it's very easy. Once you have one section, it's very easy to go to a general section, right? Because you just write your null vector P as, let's say, for example, this Poincaré section times some function that depends on x. So that can bring any section of the light cone to any other, right? Just by local rescaling of P. Okay. So if you do that, now it's another easy exercise that you should do. The induced metric now on this more general section is just omega x squared delta mu nu dx mu. Okay, so it's just a Weyl transformation of flat space. So this factor omega is corresponds precisely to this Weyl factor that appears here in the other metric. Okay, so you need to do this exercise. It's just, this is the formula. Take the differential, and because P is null, you will get this metric. So in fact, by taking different sections of this light cone, we are considering all possible conformally flat manifolds. Okay. But since we know how correlation functions transform under Weyl transformations, this tells us how you should define directly operators on the full light cone. So I'll define primary operators on the light cone such that, so O of this point P scales homogeneous. So if I put here some lambda, this is going to be lambda to the minus delta O of P, right? Where delta is the scaling dimension associated with this operator O. Okay. So this follows naturally from there, but let me show you more specifically why this is natural. So the big picture is now the CFT is going to be defined on this null cone. So the operators will be labeled by null vectors in d plus 2 dimensions. And then once you want to know some physical correlator in a specific physical space, you just restrict to the section that you want. Okay. So for example, suppose you want to know O, some correlation function on RD, right? Some physical correlator in RD. Okay. So you just go here, compute the correlator in this embedding space, in this null cone, and then restrict. You go to each point Pi, you replace it by P of xi. Right? So you just compute each operator in this section. Okay, that's the rule. This also moves. You should have told me that. What? Yeah, that's true. Okay, so let's again compare this with the general section. Okay, so suppose now I want to consider my correlation function. Okay, well, this is obvious, it's always the same. So, but now this is important, it's different. I'm not going to consider in flat space, I'm going to consider in a Weyl transformation of Euclidean space. Okay, so the metric will be omega square of x times delta mu nu. Okay, so a correlation function in this different background. So I just use the same rule. Okay, so what is this? Is the correlation function in the embedding, but then restricted to pi equals to omega of xi p of xi, where this p of xi is the Poincaré section, right? But now you see, by construction, once you compute this restricted to this generic section, you can use this homogeneity property of the operators to bring out these factors of omega. So you just get omega to the minus delta 1 at x1, dot, 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 and then the correlator in Rd. Okay, so with metric delta mu nu. Okay, but this is precisely the formula David wrote for the transformation of correlators under Weyl transformations. Right? When the metric changes by a scale factor, the correlator of scalar primary operators transforms this this way, where delta is the scaling dimension. Okay? Yes. If you are considering scalar primary operators, so the Weyl anomaly changes the partition function, right? But if you define, the usual definition of correlators is the path integral divided by the partition function. That dependence actually cancels. So for this, it's still true. I'm getting a lot behind schedule. So how much time do I have?
15 minutes.
15 minutes. Okay, so, but what's the conclusion? The conclusion, so how can I do this? The conclusion is that now I will always be considering correlation, conformal field theory living on this space, and the way to impose conformal invariance is just imposing Lorentz invariance plus this scaling property, this homogeneity property of each operator. So conformal invariance will just be equivalent to this SOD plus 1 plus homogeneity property. Okay, so let's do an example to see this at work. Actually, this is exercise for you. I'll just do the simplest case. You should do the others. So let's look at two-point function. So let's take two operators, P1, O2 at P2. What can it be? Well, it must be Lorentz invariance. So there's only one possibility. It must depend on P1 dot P2, nothing else. Cannot depend on anything else. Actually, it's better to put a -2 here, because if you do that, then in the Poincaré section, this reduces to x1 minus x2 squared. Okay, So you see, both P1 and P2 are future-directed null vectors, so their inner product is negative, so it's good to put the minus. So that's just normalization. So we already satisfied this one, it was trivial. Now let's try to satisfy the scaling. Well, in the first one, that tells you this must be raised to minus delta 1. And now when you try to impose the second one, either it works or not. You don't have any more freedom, right? So it tells you that the dimensions must be the same. Otherwise, it must be 0. Okay? And that's it. Well, there's a constant which you can choose, or you can set to 1 by appropriate normalization of the operator. Right? So this is exactly what you saw in David's lectures. So you should do the other exercises, so 3-point and 4-point, and recover with much less effort everything that you know about the scaling of 3-point, how the conformal, the structure of a 3-point function of scalar primary operators, and also of the 4-point function. Okay? So everything appears very naturally from these two properties. Okay. So I should also discuss vector primary operators, because I think David promised I would explain that. So here it's very similar. So now your operator will have an index. So it will also be a vector in this embedding space. And you keep the same homogeneity condition. Okay, so this is the same. But now you add an extra condition, which is orthogonality. So you impose that the operator has to be orthogonal to this null vector at the same point. So this is basically telling you that you want this vector to be tangent to this null cone. And now what is the rule to actually compute physical correlators? Well, okay, let's not do that. What's the actual rule? It's the same. You just take, so if you want some, the physical operator, so I don't have to define a correlator. So the physical operator, O mu of x, for example, is just, you just take your embedding space operator, and now you restrict to the section and also project this index, right? And how do you project it? Well, with a natural thing. You just take your parameterization of your section and you just project the indices to the section, okay? So this is, if you want, restrict to section. Okay, so this is general. You can do it in the Poincaré section to see what kind of matrix appears here, to understand more explicitly what is happening. But this works in general. But something non-trivial follows from here, is that there is a redundancy. So if you take your operator OA at point P and you just change it by adding anything proportional to PA, so any other function of P times PA, this will not change the physical operator, because this is P will be contracted with the derivative of P, and because P squared is 0, this is also 0. Okay, so this is a redundancy. And the basic idea is that you really need it, because remember, the physical operator at D components, right, but the embedding one has d+2 components, right? So you need to subtract one component from orthogonality and another component from this redundancy. Okay, so this is the way the embedding space realizes the physical d-dimensional vector operator. Okay, so another exercise. I should not move here. Any question about this? Well, that's a very open question. I think this is really the natural thing to do. You don't have, I think basically it's the only thing, because to impose any other constraint, you would have to introduce some other structure that would, there's no other vector at your available, right? So if you choose another vector, you will like choosing a special vector and breaking this SOD invariant. So again, let's do the 2-point function just very quickly. So let's say you have the 2-point function of some vector operator. So again, what can this be? So we already know that to satisfy the scaling property, you have to have the inner product to the power delta. But now you have these two indices, A and B. So what can you do with these indices? So one thing that you can do is to put the metric in the embedding space, eta AB. Another thing you can do is to put the vectors themselves. So let's say P2A, P1B. And if you want to preserve scaling, you should divide by P1.P2. Okay. And so plus. So in principle, you could also start putting terms like P1A, right? But those are these redundant terms, right? Because if you put the vector raised to the index at the same point, it's one of these redundant terms that projects to 0. Okay, so this is redundant, so we don't have to write it. It's just a waste of time because it will not contribute to physical correlators. So these are actually the only two terms you can write which are not redundant. Okay, so now the only other thing that I still didn't do is to satisfy the orthogonality condition, which must be satisfied both at point P1 and at point P2. But it's very easy, right? If you contract with P1A, this term gives P1B, and this term also gives P1B. So you just have to put a minus sign here. Okay, and that's it. And so you see, the game is very intuitive. You can, you should now take this formula and bring it down to the physical space and compare with the expressions that David showed you last week. Okay, to convince yourself that this works. And I have to do now some trick which is not very pedagogical, but in the interest of time I have to do it. So if I want to do tensor, I just have to put more indices. So I'll put A1 up to AL, A1 up to AL. So this will be a spinel primary operator, where so the condition that it's spinel tells you that O should be totally symmetric and should also be traceless. So if you contract eta AB with two indices of O, you should always get 0. Okay, so those are the two extra conditions when you go from vector to higher spin tensors. And this condition is the same, so it has to be orthogonal in all of its indices. Well, it's symmetric, so it's enough to be 1. And here it's the same, right? You just, if you want mu1 with more indices, you just project in each index with one of these Jacobian factors. Right? That's the same rule. And here the redundancy is bigger now, because here you had a generic tensor with L indices, and any function proportional to PA1, so this function can still have L minus 1 indices, will still be redundant. Okay, so this is bigger redundancy. And okay, now exercise for you is to do the 2-point function. So you should do A1 AL of P1, B1 BL, B2, and you should also do the other, which is two scalars, and one spinel tensor. And should ask me if you have problems with this. You should come and ask me. Questions?
How about
Fermions. It's also possible to do fermions. Yes. Yes. Basically, you define, it's some similar story. You define some fermion in this embedding space, and there's some generalization of this orthogonality when you contract with some X, contract with some gamma matrix. Yeah. So, what should I do? How much time do I have?
3 minutes.
Okay, so okay, I can say this just to, it's more or less close. So since I don't have time for much more, let's just get some intuition that will be important for the next lectures. So consider another section. So let's consider what I will call the global section, which you can define like by the condition that P mu square sum, so mu from 1 to d is equal to 1. Okay, some other condition that tells you how to cut. So this can be also parameterized very nicely. So again, I'm using this this notation. And so the parameterization here is cosh tau omega mu minus sinh tau, where this this omega mu, it's a unit vector in d dimension. So it's a point on a d minus 1 sphere which is contained in Rd. Okay. So you should analyze this section, parameterize this way, and in particular show well, verify that this obeys, I mean, it's a null vector and it obeys this constraint, and also derive the metric. So the induced metric on this section is just d tau square plus d omega square. So this tells you that this section of the light cone as the geometry of this cylinder that was very important to study radial quantization, right? For the state operator map. So it's this cylinder where tau it's the Euclidean time, and each section is a sphere. So it has the geometry of R times S d minus 1. Okay? So this is another phase of, so it's another conformally flat space. And yeah, you should also, it's also instructive to think of this exactly as a conformal transformation. So you should check that there's a very simple relation between the Poincare section and this section, this global section, tau and omega nu, which is, you just have to rescale by e to the tau. Okay, so this tells you exactly that this Weyl rescaling factor that takes you from the cylinder to the plane is just e to the tau. Right? You should remember this from David's lectures. And okay, I had much more to say, but I'm already 1 minute over time, so I should probably stop here. Thank you. Sure. I know a question. Yes.
So here you're considering SO theta 1,1 because originally you start from a Euclidean.
Yes.
Right?
Yes.
So Weinberg, I think, has some papers where he discusses like what if you start from like Lorentz signature CFT and then you go through plus 1 and plus 1. So it's like kind of like SO d, 2 instead of
Yes.
SO d plus 1, 1. So what is the advantage of kind of like this SO d plus 1, 1 formalism with respect to either
It's equivalent. I will also discuss a bit the Lorentzian version next lecture, because it will be useful to get some intuition for the actual dynamics in anti-de Sitter space. But it's completely equivalent. You just rotate from one to the other. Actual computations are usually easier in Euclidean signature, so that's why I'm discussing this more. But in terms of this logic, it's completely equivalent.
Why not then, for example, instead of SO I mean, why not
No, it's
Euclideanize again? Because now you have like so in your embedding formalism, you started from like Euclidean and you go to a Lorentzian in one time, but then why not Euclideanize again and work only in Lorentzian but in SO?
No, that's what I'm saying. If I started from Minkowski space, CFT in Minkowski space, d-dimensional Minkowski space, here I would say everything now in R d, 2 and SO d, 2, and yeah, that the story would be exactly the same. You can just
rotate the light mode to be Euclidean also. Yeah.
Here to be SO d plus 2.
Yeah.
Yeah, that I don't think it works because I don't think that. You see, I already started Euclidean, so you mean instead of the light cone, I would consider some unit sphere. But you see, already you have to introduce some scale. The unit sphere, I mean, there must be something. Well, here it's p squared equals 0. So this only works if there's some Minkowski space. Otherwise, p squared equals 0 is a point. Yes, this was for the Poincare section. Yeah. Yeah, this was for the Poincare section. In general, you just restrict to whatever section you are interested in. Here I was looking at RD, so I restrict to the Poincare section. Yes, actually there's another. So I only discussed two sections, right? Poincaré section, this one that I called global, that gives rise to the cylinder. There's also a very obvious section, which is just P0 equal 1, right? So you just cut this light cone like that. That gives immediately SD, the Euclidean sphere. That's also an important section for some calculations. Yes?
Going back to this large end factorization, is there a similar story?
Yes. And even for vector models, doesn't have to be gauge theory. In vector models is actually much simpler, because here even the leading large n term was an infinite sum of diagrams, right? Planar diagrams, you can still make an infinite number of them. But even when you have vector values like the ON vector model, then you still have large n factorization if you think of the single trace or the single particle operators as just phi i, right? With maybe some derivatives in between. Yes?
Is there a version of this embedding formalism following twistors?
Yes. David was one of the developers of that.
Oh.
Probably you'd started, right? You really introduced this twister version, or was there something before? Yeah, okay. Yeah, for 4D it's very systematic, yeah. Because then you can so here this one is particularly good if you're interested in these symmetric traceless representations. Okay, then you can do any dimension. You just have these symmetric traceless tensors. But now, if you want to go to more complicated mixed symmetry tensors or with spinors, fermionic fields, then, for example, in 4 dimensions, it's much more efficient to do this twister. Then you can classify everything more systematically.
Thanks, Joao.
It's going to be hard. Sure.
So is it usually easier to check divergences in chord identities in the physical space than in the embedding space? For example, does
Divergence is easy.
it's sort of like does DAOA actually give me something useful? Or?
Yes.
Okay.
So yeah, it's here. So if you do d by dp a, oh, sorry, when I put the index, this will be down. So actually, it's interesting. So this condition, if this guy has dimension equal d minus 1, this condition is actually conformal invariant. You see, because this condition, why isn't this condition necessarily conformal invariant? Because this is a free derivative in the embedding. So in principle, you're taking derivatives outside the light cone, where your operator was not even defined. But in fact, if this guy has this dimension, you can show that this precise combination is independent of how you extend the field outside the light cone, and so you can consistently set it to 0, and that's